Okay, I'm back. Last time I finished up talking about radiation pressure. Now I'm going to move into polarization, which we can see in this next part of our notes. Here we go. So it tells me I should look at the electromagnetic wave again. My notes do. A lot of my notes are written towards me, not necessarily towards the students, so if you find little notes along the way that look like they weren't for you, that's probably notes to me. Again, so we're looking at this one electromagnetic wave, and this is the electromagnetic wave that would be produced by one particle moving around, where you have up and down for the electric field, back and forth for the magnetic field, everybody moving in the other third dimension for the velocity. But this is just sort of one wave. You'd typically have lots and lots and lots of particles producing this, and so the electric fields would be randomly oriented, which is what I've got badly down there. And it's meant to be shown in this diagram or this picture here. So we have sort of randomly oriented electromagnetic fields here. So we might have electric field up and down like that, electric field like this, back and forth, looking like that, randomly oriented. We call this unpolarized light. But there are ways to absorb or block certain orientations, so that only specific orientations of our electric field and also magnetic field come through. This is called a polarizer, and they're usually sheets of plastic. You can also make sunglasses out of these, and they have very long molecules stretched out on them that only allow components of the electric field that are parallel to those lines to come through. So say this was the electric fields that were incident upon this polarizer right here. This electric field E1, which is all vertical, that's all going to make it through, but E3, of course, none of that's going to make it through. It's all perpendicular to the polarizer. And only the vertical parts of E2 and E4 are going to make it through. Because of this, if unpolarized light goes through a polarizer, only half of the intensity, the incident intensity, is going to get through. And so we say E1, which is the intensity after one polarizer, is E0, the initial intensity, divided by 2. This is the 1/2 rule. If it passes through another polarizer after that, so here's our second polarizer, and this was the E1 light that's coming into it, only the component of that light that's can be written into that direction, into that new polarizer with this theta, is actually going to make it through. And so we say the E that passes is the E0, or the E that's coming into it, times the cosine of theta. If we write this in terms of intensity, the intensity after the second polarizer is the intensity after the first polarizer times the cosine squared of this angle, where the angle is the angle between the first polarizer and the second polarizer. So say we had some intensity, initial intensity, that comes into our first polarizer, where the polarizer is, all vertical, and then that comes out and we have our E1, which is going to be all vertical. Then we go through a second polarizer, which is perpendicular to that. In other words, this theta between the first polarizer and the second polarizer is 90. Well, then by the time you get out of the second polarizer, you'd have no light coming through, which is a good way to test, as somebody mentioned in class, to see if you actually have real polarized sunglasses or not. Take two pairs and cross them at 90 degrees. Number 33 is worded a little bit oddly, so let's go ahead and look at it. That is one of the problems we're supposed to be doing. So number 33, why don't we go ahead and make a separate piece of paper for this. So number 33 says that we should look at figure 3340. So let's go ahead and look at that figure real quick. So we have some incident light that's coming in, and it goes through our first polarizer. So I'm going to draw that over here. Here's our, oh goodness. For them, I think that's on a circle. So we have our first polarizer. Where oriented to the y-axis, it's got an orientation of theta 1 as drawn, where theta 1, our problem tells us, is 40 degrees. The second one, so we have a second polarizer, and I might as well draw the third one while I'm in my circles. Our second one, again, here's our y-axis, and it tells us that theta 2 here is actually 20 degrees, but notice theta 2 is from the negative y-axis, so it's actually like this. And this is 20 degrees, and then finally we're going to go through our third polarizer. And that's positive y, where again now theta 3 is actually the same as the first polarizer. So sorry, this is y. This is again 40 degrees. So it wants us to say, what does it want us to say? It wants to know what percentage of the light's initial intensity is transmitted by the system. So we have some initial intensity. Obviously, after we get through here, we have I1, where I1 is half of I2, or the initial intensity. But then when we go through the second polarizer, we know that I2 is I1 cosine squared of an angle. What we need to know is the angle between the first polarizer and the second polarizer. So let's just draw those sort of together here. So let me draw, this is just sort of a circle to get this straight in our minds. So here's y. Scan up a little bit. So our first polarizer is here, right, where this is 40 degrees. And the second polarizer, that's terrible, is more down here, where this is 20 degrees. So what we want is this angle, right? That's the angle that we want here. Well, this whole line, that's 180. So our theta here is 180 degrees minus 40 degrees minus 20 degrees. So that's 120 degrees. And so that would be what we put into this equation. So we'd say I2 is I1 cosine squared of 120. Going through the third polarizer, now we want I3 is I2 cosine squared of theta, and again we want to know the angle again between now the second polarizer and the third polarizer. Well, this is exactly the same as what we just had, so it's backwards. Oh goodness, I hate when it's trying to make decisions for me. Now we're going from a polarizer which is 20 degrees to a polarizer which is 40 degrees, but this theta is still 120 degrees. Hoping that sort of makes sense. So if I walk this all the way through, I have that I1 is I naught over 2. I2 is I1 cosine squared of 120, and I3 is I2 cosine squared of 120. It's a little messy right there. See if I can clean that part up a little bit. But again, this is I3. So we can substitute all this back in for, we can find I3 in terms of, we want to know I3 divided by the initial. It wants to know what's the percentage of the light's intensity that's transmitted all the way through. So we can go through and find that number. Okay, so going back, we talked a little bit about this in class, that when you do have light that's reflected off of a flat surface, it's partially polarized to the plane of that surface. And so when we have, say, light come in to, say, water or ice or something like that, and we get a nice flat surface, we're going to get the light which is sort of polarized, or at least partially polarized, in that plane, and so that we see that as glare when we wear sunglasses, which are turned 90 degrees from that glare, which should help block that sort of flat light from getting through, and it's easier to see. The other part I wanted to cover in this lecture, this video, is about what we're doing in lab. Wednesday's lab already did this. Monday's lab, we'll do this when we come back from break, is the law of reflection and then the law of refraction. So the law of reflection is the easiest law that exists in physics, in my opinion. If you have some reflecting surface, let's say a mirror here, which we've drawn as this flat line. Mirrors, I often draw hatched marks on the back of them to show this is the side that's not reflective. And then you have some light, which is incident on this mirror, which I have drawn as this line right here. There's some normal at that location, which is a line which is 90 degrees, and there's a reflected ray that comes off. The angle that the incident ray makes with the normal, which we call theta I, has to equal the angle that the reflected ray makes with the normal. This is theta I equals theta R. This can get a little more complicated, like in number 49 in the textbook. I'm not going to go into that. When you might have two mirrors next to each other, and you have to figure out what angle things come out. It's just a lot of geometry. Go ahead and look at number 49. I think you'll probably be able to do it. The other one is the law of refraction. This is when light comes into hits some interface between two transparent media. So say you have air and maybe water, where light can travel through both of them. But as the light comes in from the air, let's say, and hits that interface, it will bend and make an angle, which is, if it's going actually from air to water, will make a smaller angle. And again, these angles are measured to the normal. Light could go either way, so I often sometimes draw them the other way. You could have light coming from the water into the air. You could have the light coming from the air into the water. Each of these have, all media have called an index of refraction. And it's the ratio of the speed of light in a vacuum to the speed of light in that medium. Light goes, the speed of light, according to the 2.9979 times 10 to the 8 meters per second in a vacuum, and it goes very close to that in air. But as you go into more difficult mediums for the light to go through, it will move slower. And so all media have this index of refraction. Again, it's material dependent. What Snell's law says is there's a product between the index of refraction and the sine of the angle that the light will make inside that medium. And this product is constant as you go from one medium to another. Let's look at some examples of that. So again, both media have to be transparent to the light. The light can't be absorbed in there, or at least not completely absorbed. Some of the light probably is still reflected, but some of it is going to be transmitted. Here I'm showing a diagram of where the light is coming from a material that has a higher index of refraction to a material which has a very low incident of refraction. We see that this is still Snell's law. You have a high incident of refraction, index of refraction, and you have a smaller angle. But then when you move into a region where you have a lower incident index of refraction, you'll have a larger angle. So theta 2 has to be greater than theta 1. Mathematically, we could roll through this, say we know theta 1 is 35 degrees, we know our indexes of refraction, we can solve for theta 2. How about I went through and said, well, what if theta 1 was 41 degrees? If we run through that and do that math, then all of a sudden theta 2 becomes 80 degrees. If we bump that up to 41.8 degrees for our incident angle in this higher index of refraction material. Now the angle is really big. It's 88.9 degrees. Just to draw that. So here's our interface. Here's a normal-ish. And then we have, say, our, oh goodness, we have our incident ray. Make that a little bit. Here's our incident ray, 41.8 degrees. So now 88.9 degrees, that's like, I don't even know if I can draw that. It's very, very close to the media, to the interface, right? Here's 88.9 degrees. What's going to happen if this angle gets a little bit more deep? If we have it maybe a little bit larger, you're going to end up with a transmitted ray, which is essentially along the interface. It can't be, theta 2 cannot be larger than 90 degrees because that's just a reflected ray. So when you go from a medium N1 to N2, where N1 is greater than N2, there's a critical angle. And if light comes in at an angle which is greater than that critical angle, all the light's going to get reflected, and you're actually going to use the law of reflection instead. If it comes in at exactly at that critical angle, then you'll get what we call total internal reflection. This is if our theta is equal to the critical angle. You'll get total internal reflection where all the light basically sits there and it stays inside. Or actually, even if it's greater than that, it all is going to stay inside that medium. For our situation here where NG at 1.5 is a real good approximation for the index of refraction for glass into air, the critical angle is basically 41.8 rounding, and you end up with a theta 2 of 90 degrees. Fiber optics uses this idea of having light come in at angles which are greater than the critical angle, so that everything of the light just basically bounces around inside the fiber and none of it transmits out, keeps the light signal in the fiber. At this point, I kind of did want to look at the PhET diagram. So the lab that the students are going to do on Wednesday, since we're not going to be able to do an in-person lab, uses this sort of diagram, or this simulation. So here we have a laser, which we can change the color of the laser. Here, I'll turn the laser on. Change the color of the laser. Here's really violet. Here's some pretty green and some red. So we're changing the index of refraction. We're changing the color of the laser. We can also move this protractor over here so we can actually measure. So we could put this, and so that's an incident angle of 30 degrees. Notice that the reflected angle is also 30 degrees, or pretty close to 30 degrees. And then we could measure our transmitted angle, or the angle down here in the glass. What's interesting is, watch this really quickly, the light transmitted angle down here is just shy, it's right around 29 degrees, but if we watch it as I move this wavelength all the way from the red all the way to the blue, notice it actually moves slightly. You get a slightly different angle when you go all the way over to the purple from the red. And that's because there is a color dependence in index of refraction. And there's slight variations because of wavelength. The index of refraction for violet is more than the index of refraction for red, and we can see that too. It's telling us the actual numbers on the screen. For glass, it's 1.519 for violet light, and only 1.499 for red light. And so number 54 has you work through some of that, telling you the blue index of refraction of a specific material and the red index of refraction, and having you go and figure out what the actual angle that's being transmitted for blue and the angle for red. So refraction is wavelength dependent, slightly wavelength dependent. Reflection is not. Reflection is wavelength independent. This is something that astronomers have to deal with, or basically this is why one of the big reasons why astronomers no longer use lenses in their telescopes for the main collector. We almost always use mirrors. It's because we don't like to have red light and blue light basically bending in different ways through the lens. The last thing is just that it is possible to completely polarize through reflected light if you hit your interface at just the right angle, which is called Brewster's angle. Brewster's angle is the inverse tan of the N2 over N1, where this is N2 and this is N1. You can get, all of the reflected light would be polarized in the plane of the interface. Transmitted light is only partially polarized. All right, so that's pretty much all of chapter 33 between these two recordings. I'm hoping I can get them to upload, and you guys have a chance to look at them.